Okay, good day, everyone. First of all, just want to check you can hear and see us. If there is a problem, please write in the chat. And welcome to our webinar on the Iscan advantage in applications. My name is Nare Gabrielian, and I'm a product marketing manager at CGD, and I will be your moderator today. And if you may go to the next slide, please, Peter. This is the fourth session of the webinar series organized by CGD. I don't know if you've joined the previous ones, but they are all available on our website and on YouTube. And if you have joined, then you know how good they are. So just to start off with some ground rules, if we may go to the next slide, thank you. We ask you to keep your microphones muted and post your questions in the chat. If it's relevant to a specific slide, please mention in your question which slide it refers to. And I will read all your questions at the end of the webinar, and Peter will answer to them. Also, as with previous webinars, we are recording this session, and there will be a link to the recording, and we will send it to you after the webinar. And now I'd like to introduce to you our host of today's session, Peter. So Peter is CGD's Director of Application Engineering. He has 25 years of experience in the field of power electronics devices. And currently, Peter is leading our application engineering team at CGD, helping customers and partners to integrate our devices into new designs, as well as develop reference and evaluation boards to demonstrate the benefits of CGD's technology. Peter, I'll just hand it over to you now. Thank you.
Okay, thanks, Nara. Hopefully everyone can hear me okay. First of all, welcome everybody. Thanks for joining us today. So what we're going to cover here in about 40 minutes is a bit of an introduction into ICeGaN and also how to get the most of ICeGaN in your application. So what we're going to cover is what needs to be considered to implement ICeGaN into your design, adjust performance, and also introduce some of the not so obvious benefits and how you can get the most out of those in your application too. So in terms of today's content, the first two items here have been covered by my colleagues in previous presentations, tutorials, as Nora mentioned earlier. So I'm just going to cover those relatively briefly, but if you do have any questions, do pop them in the chat and I can cover them afterwards. Today's tutorial is going to be more on how to design in and how that applies to all topologies. So I'm going to be touching on various topologies, but a lot of what we talk about here is applicable to all types of topologies, all markets, types of products that you would consider GaN for. And really what we're looking at is from a kind of device outward. I know some of our previous tutorials were talking more about the inner workings of ICeGaN and how to get how that delivers certain features. In today's tutorial, we're just looking out towards the application. So in terms of what we're going to cover, we're going to introduce ICeGaN briefly, talk about the devices available and the packages available. Then we're going to go into, we're going to introduce the Cambridge GaN devices first, a product portfolio, and then ICeGaN, and then we're going to get onto the application side. First of all, covering available hardware. So hardware we have available on our website to help you get up to speed using ICeGaN in various applications. And then we're going to go through a number of different areas covering how to introduce ICeGaN into your design, whether you are simply, you've currently got a silicon device, silicon carbide device, and you want to upgrade to the benefits of GaN. We're just going to cover that. And then we're going to go into some of the details about how to connect ICeGaN into your design. So the power supply needed, how to control turn off, turn on, and operation in the third quadrant. So when the device is reverse biased, operation of our current sense, and finally on VDT immunity and use of the ICeGaN Miller clamp. So let me just make a start. First of all, on Cambridge GaN devices. So we were founded by Giorgio Longobardi and Florian Udrea in 2016, primarily to bring products to the market that accelerate adoption of GaN, making it easier to adopt GaN. Principally, making it easier to design power conversion systems with GaN technology. So we're a spin out from Cambridge University, and we launched our first 4 devices in March 22, so APEC 2022. And we'll go on to what those 4 initial devices look like a little later. So today we're based in 5 locations. And I have a hugely experienced and talented team of people with a shared goal of doing their part to help climate change and reduce energy waste. So next couple of pages, we're just going to talk about ICeGaN, and apologies if you've been part of the previous tutorials, but this is kind of a key kind of enabler to some of the later discussions. So it's helpful going through it here. So ICeGaN, what is ICeGaN? First of all, it stands for Integrated Circuit E-Mode GaN, and is a HEMT. So Integrated Circuit E-Mode GaN. What it means in practice is that we have integrated certain features into GaN, so they're monolithically integrated. So a gate interface circuit has been integrated to solve issues with standard E-mode GaN, but without introducing any or without impacting GaN's performance. Ultimately, we address with ICeGaN a number of concerns, issues with traditional E-mode GaN. So low turn-on threshold, sensitivity to voltage transients, low VGS range, and also a need for GaN-specific drivers. So from an electrical engineering perspective, what you see here in our block diagram is well, most of the pins shown there are instantly recognizable. So we've got a gate pin, a drain, a source, and a Kelvin pin. All of those you would recognize from a normal MOSFET, and in our case, they do exactly the same thing. One point to highlight here is from a thermal interface perspective, of course, GaN has its thermal interface down to source, not up to the drain, as you would find on MOSFET. So from a thermal perspective, what we try to do in our application is have a really low impedance connection between source and the ground layer in your application. So, and in summary, I'm not going to read all the text here, but in summary, we're offering with ICeGaN ultimate robustness in terms of protecting the gate, real ease of use. So, you know, a simple interface without special drivers needed, and protection to make sure when you want the device to be on, it stays on, and when you want it to be off, it stays off. Without compromising the fast switching times and reverse recovery you would expect from standard GaN. I think also one point I haven't covered on this slide is, you know, the block diagram here is talking about our new version of ICeGaN devices called the H2 series. So H2 series is available alongside our H1 series. In fact, I'll go to the next page now, which covers our overall part list. So both series are available. Offering a range of RDS on, all at high voltage 650 volts. The H1 series, though, is targeted at applications requiring high efficiency and power density. H2 adds to that really for applications which require ultimate no load and light load performance. So we've added if I go back a page, the NL3 circuit, as we refer to it within this tutorial, which is no load, low load circuit to minimize our quiescent current in gate off conditions. So just briefly in terms of the devices, so as I mentioned, they're all high voltage devices. In each group, the H1 group, the H2 group, we've got 3 RDS-ons ranging from 55 milliohm to 240 milliohm. And from an applications perspective, this covers quite a wide range of consumer product types, from low power phone chargers, USB-C, to mid power, kind of 350, 500 watt laptop power supplies, lighting supplies, even up to high power solar inverters, and even into industrial. So next, let's just look at using Iscan in your application. And as I mentioned earlier, the main items we're going to cover here, first of all, just introducing the hardware we've already got available in terms of evaluation boards, reference designs, and then going into detail how to implement into your design. So first of all, apologies for quite a text-rich page here, but I just wanted to give a full view here of what we've got available. Do visit our website for more details. What this lists is all of our evaluation boards, reference designs. Many of them are available now. Others are going to be available soon using the H2 series. And mainly we're covering half bridge, which can form a key part of many topologies. We've got a number of quasi-resonant flyback solutions here, LLC and PFC evaluation boards and reference designs. What I'm going to do during this tutorial is at any stage which takes data from one of these evaluation boards or references one in particular, I'm just going to put a small note on the upper right hand side of each page just to show where that data is coming from. And if there are any questions about that, do drop them into the chat and I can cover them later. So if we move forward now and look firstly at one of the questions we often get asked, which is how do I introduce Iscan into an existing design which has silicon MOSFET devices, even silicon carbide. So here we're just looking at a low power example. The references up on the right hand side just point to an evaluation board and a reference design, both at 65 watt. And what we show here covers a quasi-resonant flyback simplified circuit on the left hand side. So we're not showing the rectifier stage, we're just showing from DC the switch stage through a coupled inductor out to a voltage out. And what we're showing on the left-hand side is the simplified schematic. The right-hand side is an extract from our our ECAD tool, PCB design tool, schematic tool. So it's an actual schematic showing what many of you will recognize as a typical MOSFET with a Kelvin connection. And in this case, with a quasi-resonant flyback, what is usually used to monitor current in this kind of application is as a source connected sense resistor. In this case, it's 250 milliohms. What we're going to do, I'm just going to change over now, go to the next page and just show how we would change this to implement Iscan. And what I'm going to highlight in particular is the commonality between what you see here and the one additional pin, which is VDD. Maybe if I turn my laser pointer on, this is probably a good time. So just highlighting this connection, which is a VDD connection and decoupling capacitor, which is required by Iscan to power the internal integrated circuit. As you can see, all other pins are carryover. So current sense is optional. If it's not being used, you would connect current sense directly to source. But the Kelvin, the gate, the drain, the source are all as you found on the MOSFET example. What we would require in addition is the VDD supply. Typically, what we find though is the VDD supply is already included in applications like this, where you've got a driver or a controller which also needs to be powered, which of course is going to generate the VGS to turn any power device on. So what we recommend is that you reuse that to power Iscan. and that would mean really the only additional component that is required for ICeGaN is an additional decoupling capacitor. So really the message is very straightforward here. I mean, really to change from silicon carbide to GaN using ICeGaN, it simply requires an additional passive component, a decoupling capacitor. So now let's look at the physical connections required of ICeGaN. So first, touch on what we've just talked about there, the VDD supply, which is what we refer to as our power supply powering the internal circuits within ICeGaN. That is a voltage supply which can vary between 9 and 20 volts DC. We've done some additional testing to take that to look over 20 volts, but from a dead sheet perspective, to ensure robust operation, do keep that voltage between 9 and 20 volts. That fits in very nicely with what you're typically going to see on drivers, MOSFET-based drivers, controllers, that kind of device. So you can very easily reuse it to power ICeGaN. The current consumption, both operating and in quiescent mode for our H2 devices, is shown here. So 800 microamps, 0.8 milliamp when operating, and down to a super low 100 microamps when in quiescent mode. So when the gate is low, the device is off. So this is an enhancement mode device. The current consumption on VDD is exceptionally low. For most cases, all you need is a decoupling capacitor, and we would recommend a 0.1 mic 50 volt MLCC capacitor. That can vary a little if you're going to power ICeGaN with a bootstrap circuit. You'd need to consider other things like the hold-up time and so on. But because of the 100 microamp quiescent current, that is a relatively straightforward exercise. Because it varies very much from different applications, for different applications, for different controllers. I'm not going to cover that here, but we can provide more detail if anyone would like advice on how to design a bootstrap circuit. But next of all, I'm going to look into gate control, how we control the turn on and turn off time. So first of all, just to touch on the voltage range. So unlike normal GaN devices, our ICeGaN device can tolerate an input between 0 and 20 volts DC. And our switching threshold, so VGS threshold, is a very MOSFET-like 2.9 volts. So typical GaN is around 1.7 volts. As I mentioned earlier, one of the issues with traditional GaN is its sensitivity to noise. A small amount of noise can get above that tipping point or the switching point and cause problems. I mean, of course, we could still have problems with 2.9 volts. It does make things considerably easier though. And we'll go on to some of the internal features of ICeGaN, which really provide a significant benefit when it comes to making sure that the device doesn't turn on when it's supposed to be off. In terms of a couple of key points when it comes to gate control, the off voltage is 0 volts. So you don't need to provide a negative VGS to hold ICeGaN off. Another super key point for ICeGaN. So really, 0 volts, hold it off and it'll stay off. Go above the switching threshold, 2.9 volts, and it will turn on. We recommend, however, just for full design margins, that we have, or customers provide a minimum of 9 volts permanently to hold ICeGaN on. So the minimum VGS voltage is 9 to 20 volts. So minimum is 9 volts. Final point here is the ability to control the DVDT or slew rate. So that is very easy, not unique to ICeGaN. You know, typically you would vary the gate resistor to adjust your DVDT or switching time. That is exactly the same with our device. So even though we've added a interface to improve various aspects of GaN, we have preserved the ability to vary DVDT, and I'll show some examples shortly. What you can also do is vary the DVDT by adjusting the VDD voltage. So by combining these two, we can see quite pronounced variation of on-time DVDT. Ultimately here, you know, the ICeGaN device can be powered by almost all MOSFET drivers, existing MOSFET drivers, further adding to our ease of use. So I'm just going to go into a little more detail on the turn on. So I'm bringing up the block diagram on the lower left, and I've just focused in there on our power hemped device, just to show some of the parasitics around that. So if we consider looking at this from outside, the waveforms on the right hand side there show the external VGS, external VDS. So it's quite small text, but the full sweep on VGS goes from 0 volts up to around 20 volts here, and VDS from around 400 volts down to 0 volts. So just going through the switch on stage, first of all, of course, VGS is going to start at 0 volts, and as the driver turns on, VGS is going to start to rise, and as it rises, it's going to start to charge the ICeGaN internal circuit and also CGS inner, as we're showing here, which is the parasitic capacitor between gate and source. And that stage is going to happen reasonably quickly. So we're going to go from 0 volts up to that point around 3 volts. Sorry, around 2.5 volts. As we get to that point, we're then going to reach the point where our VGS threshold is met and VDS starts to drop. So VGS threshold is met, device turns on, VDS then starts to drop, and then ICeGaN internal circuit charges CGS inner, but also discharges CGD inner. And this discharging process is completed when VDS is 0 volts and VGS is greater than 6 volts. So that that transient on VDS couples through CGD inner, as I'm showing here on our zoom in. As a consequence of that, we see this knee here, and as we reach equilibrium and those capacitors are then charged, we get to the point above 6 volts where the inner voltage or gate voltage is clamped at around 6 volts, and IGS will continue to charge the internal circuit to the VGS of the driver. So in our case, that's 20 volts. Now, on this slide, we're going to look at some switching transitions in more detail. In this example, as I mentioned earlier, because you can adjust the control based on the gate resistor and also the VDD or VGS voltage, what we're showing here is based on 10 ohms and 9 volts, respectively. So the waveforms are taken from a bridge application. So just included a reference here to one of our half bridge application boards. And this is showing relatively, well, it's kind of mid-range DVDT, so around 60 volts a nanosecond DVDT, and we're switching 400 volts. So this is our VGS rising, and a corresponding, as this is the low side device, then a corresponding turn on of the device and dropping of VDS. And you can see here nice clean waveforms first of all, and also very little, well, so certainly no evidence of false turn on, but very little noise as a consequence of this switching. So we see a nice turn on and turn off transition. Now we're just going to look at how we can vary. I mentioned on this slide that we've got around a 60 volt per nanosecond DVDT. Here, we're just going to go forward one again. If I can go here, here we're just showing how that can vary across different configurations. So of course this is going to vary for your application. It's for indication only. I think one big factor is going to be the choice of driver, but it's really to illustrate the point that you can see very large variation between a low of 2 volts a nanosecond way up to 123 volts a nanosecond. So the slew rates here are using our 55 milliohm device, and we see significantly faster transitions using our 130 and our 240 milliohm devices, with a corresponding reduction in COSS, as you'd expect. But really, what we're showing here is that you have very good control to adjust DVDT for your application. So if you want to slow DVDT down for an EMC issue, following testing, then you still have that facility. In fact, more than likely at that point, when you're in EMC testing, you'll already have a fixed VGK voltage as it's shown here. You probably wouldn't redesign that, but at the design stage, you've got the facility to change the gate resistor and VGK, so you have the full gamut of variation. At the EMC test stage, more than likely you've got your first prototypes. The VDD VGK is going to be fixed, but you still got quite a large variation of DVDT based on the gate resistor. Next slide, we're just going to look into one case where we look at quite an aggressive case, which is 10 ohms and 20 volts. Still using the 55 milliohm device, and here showing first of all, if we look at the VGS waveform, we show a particularly fast rise time. Just to put it into perspective, that initial rise time there is around 6 nanoseconds. Then we see a small dip at this point, which corresponds to the same point on the previous slide where the VDS voltage drops, and then through the CGD capacitor starts to impact the rising which has been taking place on the VGS. As you can see here, there's minimal impact, but it's just to explain what that transition is all about. So no impact to the switching transition on VDS. What we can see here is a nice clean transition. There's a little wobble when it hits the floor. It's relatively small, and in this case, a small a little PCB optimization should resolve that. Key point here though is the VGS and VDS transitions are particularly fast and smooth without any occurrence of false switching. If I go on to the next slide, we're just going to look at using ICeGaN when reverse biased. So in some applications, you would need to consider that, particularly in PFC. So in the application here, this is valid for many applications, but in a totem pole PFC, the one that we're showing here, we would see a case in between the fast devices turning on. So initially we would charge the inductor by turning on the low side device, and then we discharge into the capacitor by turning on the high side device. Clearly we can't have both devices on at the same time, and therefore we're going to have a dead time. What we're showing here on this oscilloscope plot is the dead time. And in that dead time, what we're going to see is this high side device conducting in reverse. And we're just going to show how ICeGaN differs from conventional E-mode GaN devices in this regard. So while in reverse, if VGS is larger than VGS threshold, then ICeGaN operates as normal, so it operates in the ohmic region. When VGS is less than the threshold, so the device is off, then we say it's operating in pseudo body diode mode, where we would have a VF, which is your typical kind of forward conduction voltage. In the case of ICeGaN, in the case of other E-mode GaN devices, this is going to vary dependent on the applied VGS. Now, going back to one of the earlier slides, I mentioned that for ICeGaN, we only require a 0-volt VGS, and therefore we can look at the next page, talking about or referencing our data sheet and looking particularly at the reverse conduction characteristics, and compare ICeGaN versus conventional E-mode GaN. So here we're just looking at conventional E-mode GaN to determine the VF, the forward voltage, to determine power dissipation in this particular stage. So for conventional E-mode GaN devices, particularly in this kind of application where you've got connected them source to drain, they're going to be experiencing large dV/dt transients. Then typically a conventional E-mode GaN would have a negative VGS voltage to make sure the devices do not turn on when they should be off. And if we then apply that to the data sheet, we can see that essentially the VF is shown here as around 4.7 volts. There is a little variation over temperature. The one on the right hand side shows characteristic for 150 degrees C, left hand side 25 degrees C, but ultimately so it's around 4.7 volts, which if we put into the application that I showed on the previous page, let me just go back to that. Go back to that briefly. So this is the 350 watt totem pole application. If we put these numbers into that application, this is an established formula, then we can calculate the dead time power loss of around 500 milliwatts. And then if we compare that with ICeGaN, so if I go forward to this page, so this is again taking data from our data sheet, same figures really. So reverse output characteristics at two different temperatures. In ICeGaN's case, though, we only go down to 0 volts because we don't need to go any lower, and really the same conditions apply as the previous page. So the gate voltage is going to influence the forward volt drop. In ICeGaN's case, though, with a 0 volt gate to ensure the device stays off, the forward voltage is going to be around 1.7 volts. Again, it gets lower with higher temperature. And therefore, in this particular application, the dead time loss is going to be around 200 milliwatts, showing quite a healthy reduction from quite an innocuous change, quite a small change. So, simply biasing the device at a lower voltage can have a direct impact to power loss. So that covers really how we control ICeGaN in both forward conduction and reverse conduction. And now we're going to look at current sense. So in ICeGaN, we use quite a neat solution, quite a simple solution to providing current sense. The block diagram on the left-hand side, I've just zoomed in a little just on the power HEMT, and I'm just showing the sense HEMT, which runs almost parallel to it. It's not quite parallel because the source of that sense HEMT is taken out to an external pin. And what this does is provide a smaller current that is proportional to the current flowing through the power HEMT. So for the current flowing through the power HEMT, we'd refer to that as ID. We'd have a proportion of that flowing out of the sense HEMT, and we refer to that as ICS. And dependent on the sense resistor that you connect to the CS pin, then of course you're going to get a voltage dropped across that sense resistor, which is proportional to the drain current. One additional benefit, just to highlight while I'm on this page, is that because the power HEMT and sense HEMT are both monolithically integrated, the thermal disparity between the two is extremely small. So they track each other very nicely when it comes to normal variation over temperature, and therefore as the power HEMT RDS on changes with temperature, that happens to ICeGaN as it does with all GaN devices, you will see a corresponding change in the sense HEMT, and therefore the tolerance according to temperature is very, very good. Next page, I'm just going to look into a little more detail at current sense, particularly that ratio, the proportional ratio between the drain current and the current sense output. So this varies according to our different devices. As I mentioned earlier, we've currently got 4 RDS ons, and each of those have a correspondingly different CS output current. So that, as we're showing here, from our 55 milliohm down to 240 milliohm, the output varies accordingly. So from 2.2 milliamps an amp, so that's 2.2 milliamps out of the CS pin for an amp flowing from drain to source through the power HEMT, up to 20.6 milliamps for the 240 milliohm device. What we're also showing in the plot is a plot taken from our evaluation board shown here. So again, it's a 65 watt QRF with our H2 devices. And we're showing here, I guess, a giveaway characteristic quasi-resonant flyback voltage waveform. So a lot of you will recognize that. Here we're seeing the resonance, and we're seeing valley switching, so the controller doing its job correctly, turning on at the low point. At that point, the device is turned on. Current will then flow into the inductor, and what we're showing here in this trace, the blue trace, is the volt drop across our sense resistor. As you can see here, it's quite a nice clean waveform, and that can be used to monitor or provide shutdown in the case of failure. Very much application specific what you want to use it for, but in this case it's used for simple control. So if for a quasi-resonant flyback, we want to turn the device off when it reaches a particular current. In this evaluation board, and we also have a reference design using the same approach, it's quite a straightforward feature, but works remarkably well. I guess the key point here is the ICS is proportional for our various devices, is fixed for that device RDS on, and with a set resistor that can easily be used to generate an output voltage VCS that is proportional to the drain current. So the next couple of pages, let me see how I'm doing for time. The next couple of pages, I'm just going to touch on some indirect benefits of current sense. So first of all, just looking at quite a obvious change, I guess, in terms of being able to remove the power dissipation in the sense resistor. So in a traditional case, you would have the full load current going through the sense resistor, and in our application, we've calculated it here. And what we do with ICeGaN is, of course, we don't use that type of sense resistor where you have the full load current going through it. What we do is pass a very small percentage of that current. Sorry, the sense resistor current is a very small percentage of the drain current. In this particular case, on this application board, it's around 50 times less. And as a consequence of that, mainly, even though the resistor value will typically be a little higher, we see a significant reduction in power dissipation simply by moving current sense from taking the full load current. Second indirect benefit, but linked to the first one, is when we remove this sense resistor, what we do is connect our source much better to the device ground. And as I mentioned in one of the first slides, GaN devices, lateral GaN devices, we dissipate our power into the source. So any power generated by this device is dropped into the source. If you can get that as easily as possible out to ambient, so look at the full thermal resistance from junction to ambient and minimize it as much as possible, you can significantly influence the operating temperature of your device. In this case here, we're just looking at the left-hand side, which is a traditional case with a sense resistor, and just stacking up the thermal resistances between the device and ambient, and then just giving a easy view really on what the difference is. What does this turn into in real terms? What we see is over a 10-degree temperature rise difference. So ICeGaN operating in this application, everything identical, a different device in this application would run 10 degrees hotter than ICeGaN. So quite a neat solution, and of course with temperature reduction brings many benefits. You could downsize the device, go for a larger RDS on, or even accept improvement in robustness in terms of and also reliability. So we're now just going to move forward onto the final section, and I'm just going to cover an item which we haven't talked about too much before, but we have mentioned the Miller clamp in a lot of our literature. We haven't linked it too much in terms of DVDT immunity, so I'm just going to explain that a little more. So again, coming up with the showing the block diagram that I've mentioned, shown a few times so far. GaN switching time is very, very fast. We've shown on the top line here that you can easily see a 10 nanosecond transition time, and we can naturally develop quite large and noisy DVDT transients. The example that we're showing here, typical bridge, the output's open circuit, but essentially the output's going to be pulled high when the high side device is turned on. It's going to be pulled low when the low side device is turned on. And what can happen here is when your high side device turns on, the drain being initially discharged or low, you then present a very high voltage DVDT transient to this point. And if we just look at this a little closer, initially, apologies for the graphic here, but initially when our VDS on the low side device is low, then our CGS is discharged. When the high side device turns on, we present a very fast DVDT transient on the drain, which then couples to the gate of the low side device. We're showing ICeGaN here, but this applies to all transistors. So that high voltage transient couples through CGD inner, the gate here, and then charges up CGS inner. And it is remarkably easy for the voltage at this point to get above the threshold voltage for this HEMT and inadvertently turn it on. That's absolutely what you don't want to happen when this device is already on. So what you will have then is a shoot-through event. So what the Miller clamp does, this device, is when this device is off, it will provide a connection between the gate and drain. So what we do is resist any what the Miller clamp does is resist any charging of CGS. So we're much more resistant to fast transients on our drain. And the next slide, I'm just going to go into a little more, well, I'm going to go into a test case, just showing some real results of this in practice. So in this case, we present quite a simple test that varies the high side DVDT, so the switching speed of the high side device, and we look to see what happens to the low side device when that DVDT is occurring. What you can see here is we're pulling both low side devices down with a 2 ohm resistor. We've tried this with higher and lower values, but just for this illustration, we're just indicating a fixed 2 ohm resistor, which would represent the full loop from device through PCB to the driver, and then the driver through the PCB back to the device. And then we are varying the DVDT by changing the gate resistor, as we illustrated earlier. So in this plot, we show the gate resistor along the bottom, and at 120 ohms, we would have a slower switching speed, and the switching speed increases as we move towards, in this case, 2 ohms. So from our test results, we've gone from 100 ohms down to 2 ohms. And we can see in ICeGaN's case that both device, or the low side device, does not turn on. What we're showing here is milliamps consumption by our test circuit, and with both switches off, the consumption is around 5.2 milliamps. What we want to see is that remain consistent throughout this testing. And what we can see is with conventional ICeGaN, as we do increase the DVDT, the low side device starts to turn on. And what this shows here is shoot through occurring, which is represented by this increase in current. Obviously, in a real application, this can be an increase in current consumption, in power dissipation, but often it's going to result in a destroyed device. So key point here is really, the Miller clamp provides optimum safety against false turn on. So this is a monolithically integrated device, which significantly reduces the risk of increased power consumption due to a device inadvertently turning on, or severe damage caused by shoot through. Okay, so now we're going to just wrap up. So in summary, we've addressed a number of issues. Well, we've introduced ICeGaN technology, which addresses a number of issues with ICeGaN. So low turn-on threshold, sensitivity to voltage transients, and low VGS range, and also need for specific drivers have all been addressed with ICeGaN as presented here. We've resolved them all in a single package without really impacting what you want from GaN. So you want the zero reverse recovery, you want the fast switching transients. Those have been preserved. Demonstrated how easy you can incorporate ICeGaN into your design, simply adding a VDD capacitor and reuse of a power rail that in most cases you will already have. The third point really is, we covered the H2 ICeGaN series and our significantly reduced no load consumption. So we refer to that here as the NL cubed, or no loss, low loss circuit. And ultimately that brings our quiescent current down to around 100 microamps. What we also covered, we explained how easy it is to power ICeGaN and also control its switching rate, including how it operates in applications that require excellent performance when reverse biased, and particular topologies where that's key. We also talked about current sense, demonstrated how easy that is to use in an application. Just adding a sense resistor can often be is quite a simple approach, and often that's enough. But also how this our ICeGaN approach gives additional benefits in terms of power consumption and reduces operating temperature. Finally, we talked about the ICeGaN Miller clamp, and we just reviewed what the Miller clamp is, what that achieves, and demonstrated its value against false turn-on and ultimately avoiding device damage. I think in terms of the main content, that's pretty much what I wanted to cover today. I did want to just finally touch on many other materials that are available on our website. We have a large amount of support information to help you design in ICeGaN, from provision of samples, evaluation hardware, excuse me, support documentation, application notes, user guides. We can even provide the item that's referred to in the center here, an application interface board, which adapts our ICeGaN device to many common footprints. So it means that you can add, well, in a first stage anyway, add ICeGaN to a existing PCB design, so you don't even have to redesign the PCB. And finally, we have other support material available on our website. Do please pay it a visit. And that pretty much is me covered. Thank you, everybody, for listening and for your attention. And I hope that was helpful.
Thank you, Peter. We overran a little bit on time, but it was useful information. There are a few questions in the chat, so I'll go in order. Duncan is asking, in adapter application, ICeGaN should have more loss of IC at power saving mode. What's the power loss of ICeGaN during PSU operates in burst skip mode?
Well, our consumption is as shown on one of the earlier slides. So let me go back to that. It might take me a bit of time, but it's when our device is off, it's 100 microamps, and when the device is on, it's 800 microamps. The actual loss in your application would very much be influenced by the duty cycle, the burst mode, the type of controller. So I couldn't comment on that specifically, but hopefully this addresses the main point and would allow you to calculate that.
Thank you. Yeah, we can see it on the slide, the operating and quiescent currents.
Yeah.
Another question from Juju Mohammed. Sorry if I mispronounce your name. Why the integrated circuit within the GaN? Does this not generate a significant stray inductance?
Remarkably, no. It's a power device, and of course, we have high power connections between our drain and source, and really is one of my initial concerns when it came to looking at ICeGaN when I joined Cambridge GaN Devices. And actually, there's very little impact to rise time, very little impact to propagation delay, and those are the two kind of key points I was looking at when I first got familiar. And we certainly don't see impacts. We've tried ICeGaN in many applications now. We haven't seen any impact due to even remote increases in trace inductance on the gate side. It is very low current, but it's been designed to operate through the range which we've stipulated here.
Thank you, Peter. Two more questions from the same person. Have you tested this device under different types of short circuit? How long is its time leading to failure under a short circuit?
That's a very good question. That testing, certain testing has been carried out, and I can't comment on it at this stage because we've not released it publicly. All I would say is I've been asked that question before, and I think it's a key point for us to be able to communicate to customers, exactly what happens to our device, what is the safe operating area for extremely large currents, well above what we have in our data sheet. So for our 55 milliohm device, the data sheet quotes around 27 amps, and we do know we need to take that above and demonstrate results to customers. But we're not at that stage yet, unfortunately, but we will be very soon.
Thank you, Peter. And then last question is, how many repetitive short circuits can it withstand before failure? How does its characteristics vary after repetitive short circuits?
It's linked to the same testing. Yeah. So, it is the same work. And yes, it's a fair question, and we will answer it. I just can't answer it today.
Okay. We don't seem to have any more questions coming in. In that case, I will say thank you, Peter, and thank you everyone for joining today's session and for the questions as well. As mentioned earlier, there will be a recording of the webinar sent to you in the coming days and also uploaded to the YouTube channel. And I hope you found this session interesting and informative, and have a good day, everyone. Thank you.
Bye. Thanks, everyone. Thank you. Bye-bye.